Yeah. So in order to look at the theoretical background of the robot models, we start by discussing about positions, orientations, then rotation matrix, and as well as how to do the transformation matrix, how to represent vectors of position, and also we will try to see how we should represent our model by using Euler angle as well as by quaternions. What is the difference between Euler angle and quaternions? And then how do we do the transformation matrix, which we call it homogeneous? What is the advantage of a homogeneous transformation matrix? This is also what we are going to see. And then what is spatial vector notations? For example, if we have to do a model with a Newton-Euler equation, then how do we make a canonical equation which could apply to every joint? So then we see this. Then we will see also forward kinematics and the inverse kinematics, and then finally we will see a dynamic models with the two typical model approaches, which is Lagrangian and a Newton-Euler approach. These are the most frequently used modeling approaches. Now, what is point actually? Just what is a position in the space? Now we are going to talk in the space. The position in the space is a position which we represented by X coordinate system, Y coordinate system, and the Z coordinate system. And this position or this point could also be represented by or denoted by an orientation. And the orientation could be also denoted by rotation about x-axis, y-axis, and the z-axis. Yeah, as you see it here, there is rotation about x-axis, there is rotation about y-axis. So this position and orientation in general gives us it gives us complete representation of a position with x, y, z, as well as with rotation about x, rotation about y, and rotation about z. So these are what we see by point in the space of, for example, for this O x, y, z, for O1 x, O1, y1, z1, and also there is a distance between O and O1, as you see it on this figure, and this distance could be measured as P, and that is the difference between O1 and OVS actually. And this could be represented by some notations like this. Just it is a simple representation. And also the rotation could be also given by a rotation about X, rotation about Y, and rotation about Z. This is derived based on the previous equation here. X1 is a motion of X along X, a motion of X along Y, a motion of X along Z. Y is a motion of Y along X, a motion of Y along Y, motion of Y along Z, and so on. Finally, this will give us a motion which is along X, Y, and Z. This with a simple notation. Yeah, so this is the orientation, and here we have orientation notation. Actually, maybe I will talk this one later on. Okay, now whenever we talk about a rotation, just we consider rotation about X, about Y, about Z, and just these rotations have their own representation. For example, we start by rotating an object along Z axis. So when you rotate about Z axis, you are performing this operation cos sigma minus sine sigma 0, and then sine sigma cos sigma 0, and 0, 0, 1. Cos sigma, sine sigma 0 are a rotation about x-axis, minus sine sigma cos sigma 0 is a rotation. The second column is a rotation about y-axis. The third column is a rotation about z-axis. So how do we differentiate this, guys? How do we differentiate? Okay, so how we differentiate is because in the earlier slide we said there is a rotation about x-axis, y-axis, z-axis. So this means RZ is rotation along x plus rotation along y plus rotation along z. So cos sigma along x plus sine sigma along y and 0 along z. The same is true for the second column, minus sine sigma along x plus cos sigma along y plus 0 along z. For the third column, it is 0 along x plus 0 along y plus 0 along, 1 along z. So now along z, we have a unit 1. This unit 1 shows a direction of rotation. Okay, it shows axis of rotation. So we have 1, which is 0, 0, 1 here, vertical and also, vertical also 0, 0, 1, horizontal also 0, 0, 1. So this tells us we are rotating about z axis. So while we are rotating about z axis, we don't care about the rotation of x along z, rotation of y along z. We don't care about this, guys. Okay, so actually maybe just we could clearly understand this one with the model that we did yesterday. For example, just let's check our jog with the robots. Yeah. Now, just actually, for example, if we consider rotation about z, means we mark it here. So when we rotate about z, and maybe if we rotate joint 1, on this, actually, if you are looking here, and here, look, okay, on the working frame. On the working frame, when I rotate joint 1 only along z, okay, constraint along z, only what are varying now? Only the position along x, position along y, and rotation along z. What is varying is this is varying, and also this also varying. Okay, but this doesn't vary. This doesn't vary. This doesn't vary. That's why we say it is rotation about z-axis. So this is one point. Okay. Now, if we fix this rotation along y-axis, okay, then it should look like this. Joint along y does rotate, so we have to rotate it up, maybe joint. We cannot rotate joint. Maybe now I could rotate this guy, maybe joint. Now this is rotation. This is still rotation about. This is still rotation about it. Okay, so yeah, because of the kinematics, actually, I cannot rotate about the y-axis. Maybe if I make like this, I could rotate now. Now this is rotation about y-axis. But it is not only for the joint because I cannot control the others. Okay, yeah, but yes, it's clear now from the z-axis, so I think that is enough. Now, just when we come back to our theory, along z-axis, we said that the only the values along x and the y will consider the changes. Okay, the changes along x and the y positions, position of the orientation, of course, and then the z-axis will remain constant. This is actually a unit vector. It doesn't give us some value. Then the other is y-axis. So just you could see here now in the y-axis we have 1, 0, 1, 0, 0, 1, 0. So this tells us it is y-axis, just like plus sign. And here cos sigma, sine sigma minus sine sigma, cos sigma is just a representation. The same is true for rotation about x. So in the x we have here the 1, 0, 0, 1, 0, 0. And then here we have the 4 parameters which decompose into x and y, x, y, and the z-axis. Okay, so this is our representation for rotation matrix along x-axis. Okay, now one point here to add is actually we could also talk about vectors. Just a vector is only it's something you call it array in somewhere, or just you call it vector in some place. So it is a representation of the position along x, y, z, or it could be a representation also force along x, along y, and along z. And also it could be a representation of torque along x, along y, and along z. So this vector representation is a representation of the point, a representation of position or a representation of force or a representation of torque. Okay, just it could be any of them. Yeah, that's when you have a matrix and when you have a matrix manipulation, there are some scenarios actually. For example, for the rotation, you have a 3 by 3 matrix, and this is a rotation, and then you have a position, which is 3 by 1 matrix. Now, manipulating this matrix is a little bit tricky, so you need to know actually how you represent vector as well as how you represent matrix. Okay, then how you multiply vector with a matrix 3 by 3 and a 3 by 1. So how it should be ordered. Okay, so this should be noted, otherwise you cannot manipulate your robot. Okay, so in order to do that, actually what we have to do is assume you have 2 pointers. This point is, one is P and the other is P prime. Okay, just you have P here, and you have P prime, along x prime, py prime, and pz prime. It is a rotation. There is a rotation. Just assume you have one axis here, x, y, and you have also another axis, which is x prime, y prime. So assume initially you are at xy plane, and later on you rotate, okay, by alpha, and you are at x prime and y prime. So now if you want to represent this original P, with the letter, okay, just with the letter P, actually, which is Yeah, actually just here I think it's this is another representation which is moving again, okay, further from p prime to p. Then still you have some variation. Now just this time, you know, if you want to manipulate this one, you need to have a concept, okay, just how you have to multiply position with rotation matrix. So one way of doing is, you know, p is equals to a rotation, okay, you have only a rotation matrix, or rotate the matrix of p prime, okay, p prime. So it is moving from p prime to p. This means actually from the model, if we see, assume you are initially on the current position, let's say here. Now from these positions, these points, okay, from these points you want to move maybe somewhere, just let's say just you want to move somewhere here. So assume this is p prime, maybe just let's say this is p prime. Then you have these values, okay, x position, y position, z position, rotation about x, rotation about y, rotation about z. Now if you want to move this one here, then actually no, maybe let us focus on only on rotation, because let us do step by step. Okay, so now let's say this is here. Okay, let's say this is here. Now we rotate only about z axis. Okay, we rotate about z axis, this guy. Yeah, maybe just we are from here and we are maybe just we are rotating here. Yeah. Now during this time, actually I cannot notice down the axis. Yeah, but during this time, just there is a change of axis, and when we look this from the slide, actually it is there's a multiplication of matrix. Maybe no, this is not a good example for me. Maybe we go to the maybe just we go to the path editor, and then maybe just we talk it from the path editor. So now from the path editor, you have these pointers: x point, y point, z point, and you have rotation about x, rotation about y, rotation about z. Yeah. Now, in order to move, okay, from VR1 to place, okay, just between these 2 pointers, you know, just in order to move from VR1 to place, I have a change in position. Yeah, okay, maybe now let us make additional point here. Maybe, or let us make the same in order to have the same thing. Maybe we make this one also 900. Maybe this also 900. Maybe this is 600. Here is so 600. Maybe here is 1335. 33. Okay. Here also 1335. Okay, so now the position is the same. Okay, we have the same position, but we would like to change the rotation. Okay, that is our goal. So now just let rotate on, let have minus 45 degree, and maybe now we could able to see it. Just to see only what I would like to see. Maybe box 3 perhaps. Okay, now I think you see it now. Okay, so now VR1 is here. The blue one, okay. And place is this one, again the blue one. So here the red one is place, and the red one is place, and the yellow one is our VR point, okay, our VR point. Now actually just I would like you to understand it, okay. Now for both z-axis is changing, okay, for both axis, z-axis is changing. It has moved by, it has rotated by 90 by minus 45 degrees. Maybe just we make it this one 0. Just maybe let's see then to understand it better. Yeah, now when it is 0, the VR axis, okay, VR1 is the same as the axis of this, the global reference frame. This is very important, okay. Here on my left side, I have a global reference frame, which is y is upward, x is to the right direction. X is to the right direction. Just look only the blue, the cyan color, just the select one. And then y-axis is upward. This is very important. Now, if I rotate this VR1, okay, keeping all the position constant, only minus 90 degrees, then I got the in the new, actually I got the x-axis along, I got the x-axis along this y, but just there's a rotational which is 90 degrees, so it is rotating, and now I have the original x-axis aligned with y-axis, okay. The original x-axis the original x-axis is aligned with y-axis. The original y-axis is aligned with x-axis, okay. So there is a shift, okay. There's a change of axis. So the original x-axis is with y-axis, with negative y-axis. The original y-axis is with a positive x-axis. Now maybe just we keep this one 0, and just we change this one to 90 degrees. So this time again, the yellow color shows the place, and the red shows the VR point. So VR is again, it is aligned with the global reference frame. So global reference frame goes to VR, from VR goes to place, okay. So between global frame and the VR1, 0 angle on all axis, but from VR1 to place, we have a rotation of y-axis, which means the original x-axis of the original x-axis is already along the original x-axis, but the original y-axis is along z-axis. Okay, the original y-axis is now on the new z-axis. So actually, this is a mathematics, okay, that we should have to understand, and we have to manipulate, okay, during our operation. So in order to do that, you have to think actually how you manipulate your matrix, as well as what if there is a change in position. Now, maybe that is where we are failing, just to understand. Maybe let's say this is here. Maybe I put too much. Maybe now, look it now. Actually, the good thing is it shows you with arrow. Now, this is the second is place. So just you have a global coordinate system. From global coordinate system, you align your you align your maybe the initial point, which is via point, which is marked with yellow. Then the second is a place position, which is marked with this one. Yeah, maybe just for some time, let us hide this one. And just try to see this one maybe in 3D. Look it now. Okay, now here actually, if you see, there is you know how we compare this with the global coordinate system. Okay, so now you compare with the global coordinate system. So y-axis, because here is 0, so this is the arrow is x-axis. Which one is this one actually? Yeah. The arrow is z-axis. Sorry. So arrow is z-axis. The dot with dot is x-axis, and the shortest line is y-axis. Okay. So now z-axis, the original z-axis from via point has turned into the x-axis. Okay. After transformation, when we rotate only about y-axis 90 degree, when we rotate about y-axis, okay, so rotate about y-axis here, about this y-axis. When you rotate about this y-axis, the y-axis remains constant, but when you rotate about y-axis positive 90 degree, okay, just with your right hand rule, just you put along the axis of z rotation. For example, here you rotate about z axis, so your thumb shows to the direction of the orientation, or it is not to the direction of rotation, and your fingers just shows to the direction of rotation, right? So when you put your hand along the y-axis, then if you put the fingers to the rotation direction, then you see that the z-axis is turning into the x-axis, as well as the original x-axis is turning to the negative z-axis. Okay, so this is what we are going to do. Okay, just in the next slides. Okay, so now we are back to the lecture. So now for this, we have a point P, which is multiplied with the rotation, and a point vector. Okay, point vector. So now this will give you some kind of notations where you have a rotation matrix 3 by 3 multiplied with 3 by 1. Okay, So 3 by 3 multiplied by 3 by 1 is possible. Just you can perform the mathematics, so it's not a problem. So actually, that's why finally we will have a 3 by 1 vector. Okay, position is a 3 by 1 vector. So finally, you have a vector. So a vector equals to a matrix multiplied by a vector. Then it gives you a vector. Now, actually, just the other good point is to talk about the property of these rotational matrices. Actually, this rotational matrix, actually, this is also a very important point. These rotational matrices have really a unique property. From this property, one is they are actually why we are interested with the rotational matrices is they are their inversion. You know, if you invert, you know, if the inverse of rotation matrix and the transpose of the rotation matrix is the same. Okay, actually that is the good quality of these rotational matrices. So whenever you want to make inverse of the matrix, because you know matrix inversion of matrix is tricky. It's really difficult, right? Especially if you have more number of rank. Okay, if the matrix has lots of columns and rows, yeah, it's really difficult. But rotation matrix is actually even 3 by 3 matrix, inverting 3 by 3 matrix is also not easy. But if you know this concept, okay, if you know that the inverse is equal with the transpose, you know, exchanging the row and the column could simplify your life. Okay, so rotational matrices are the same with their transpose. Okay, so this is interesting. And the other is actually also the other very important is the order matters. Actually, just the order also matters. Always you have to be sure that this P prime is inverse of a rotation matrix of P actually here, because originally we said we have P equals to R P prime. Okay, so if we need to calculate a P prime values or vector, then this R should be inverted here. Okay, so we should have to invert this R and multiply on the right side of P. Actually, maybe if you remember your algebra class, you know, just the position also matters. Okay, so you don't have to put it here on the right side of P, just put it on the left side of P, because you are multiplying vector with a matrix, so then it will make a problem. So this is one way. This is one concept. The other concept is actually also just how you represent your indices also really matters. Yeah, just for example, if you say R1, R2, you know, if is equal to R, no, assume you have one R2, okay, or just assume something like this. This is, you know, specifically, this is the same with IRJ transpose or IRJ inverse. Okay, no. Yeah, because I change the order of the index. Okay, JRI is equal with IRJ transpose or IRJ inverse. Okay, because I change the order. Okay, so if you have JRI and if you have IRJ is the inverse of JRI. This is the inverse. or it is the reverse motion, okay? While you are moving from I to J, you are moving from J to I, okay? That's what it means. So the order matters. So if this is from I to J, you know, this is moving from I to J. Start at I and move to J. Then if someone writes I R J, it means move from J to I, reverse. Okay, so that's why we need to make inverse rotation. Actually, this is also a property of rotation matrix, and it's very actually interesting. And yeah, and the other point actually we should look at is now if you have a sequence of points, okay, as we discussed yesterday during the tutorial, there is point 1, there is point 2, there is peak position, there is also place position, okay? So between these points there was a transformation, okay, or there was a transformation from one frame to the other frame. And actually this has happened because of this concept, okay, which you are looking in this equation. What does this concept tells? You know, if you have provided that, okay, if you have a constant positions, assume the positions doesn't matter, but there is a change of orientation, only it's making orientation change. So this time the consecutive rotational matrices or the successive rotational matrices could be multiplied, okay, sequentially. One multiply with the second, multiply with the third, multiply with the fourth, multiply with the fifth, then multiply with n. The multiplication of all these matrix, rotational matrix, will give you one rotational matrix, a cumulative, you know, it's one cumulative rotational matrix, which you call it 0 Rn. And this rotational matrix maps the original point with the final point, okay? Just the original point with the final orientation. The original orientation with the final orientation. But these matrices should have to be multiplied in sequence of their operation, okay? Otherwise, it will mess your process or your operation. So it should be sequential in the order of their operation. Yeah. So if you multiply 3 by 3 matrix 10 times, you will get 3 by 3 matrix at the end. So it doesn't matter, just finally you will have a 3 by 3 matrix. This 3 by 3 matrix will be multiplied by 3 by 1 vector, and then you got a 3 by 1 vector, which is a position vector, okay? Yeah, now I think, yeah, actually this is what I was telling you about the rotation matrix. Now I think you will start to think about something. I expect you will start to think about what is this rotation matrix? What is this vector? Why I multiply 3 by 3, 3 by 3, and then finally multiply 3 by 1, something, yeah. Then why, you know, just something will come, and then maybe just you think that it's something complicated, you know, because you multiply rotations and position, R1, P1, R2, P2, R3, P3, R4, P4, R5, P5. If you have a changing position as well, you know, assume it's not only change in orientation, you have also change in position, okay, between successive pointers. So the position vector should become P2 equals, no, for example, Pn equals to R1, P1, R2, P2, R3, P3, R4, P4, Rn, Pn. It's really tedious, okay? It seems like tedious. So Yeah, it is very, yeah, you know, if you have to do it with a computer also, just it's letting the computer just to do some big manipulation, you know, so, or numerical computations. So it takes some memories, some speeds, performance, and so on. And then just it's a problem, right? Also, it makes some confusion because you could miss also something. So in order to avoid such things, yeah, just you have to think actually how you could combine this rotation matrix and a position vector, okay, just at one place. Yeah, but before that, just let us discuss what is coordinate systems, because you need to define your reference frames. What is the world reference frame? What is the base reference frame? What is tool reference frame? And what is the robot base? Actually, this is a KUKA robot. In the actual, in the real practice, this is from the KUKA manual. Actually, we have tool center point, which we call it tool TCP. It's a tool center point. We call it also indifector. Indifector is also a tool center point. It's also a gripper. We could call it also a gripper reference frame. Yeah. We have a flange. A flange is where you connect the gripper and the robot systems, okay, together. And a world is a world, okay. It is where you define your world coordinate system, which is a ground truth, okay, where you refer your system. Then the other point is actually base. It's this actually also we could call it work space reference frame, where you say this robot has a reference frame to this, actually just where you define your object. For example, sometimes you would like to define temporary reference frame which aligns with your object, okay, with your object. For example, if you have a rectangle, then you would like to have a reference frame which aligns, okay, with the object. That is not a world reference frame, but it is a transformed reference frame, but you could consider it as a ground or as a general reference frame, okay, as a fixed reference frame, and then generate your trajectories or something. But that is not true, because it is a computed reference frame, okay. It's a computed with respect to the robot root frame and or maybe the world reference frame. Yeah, but just you have always a possibility to configure your coordinate systems, you know, along the work part. Then when you have these reference frames, now the question is how to represent. For example, on the robot there are so many joints, for example, or there are so many joints here. For example, we could expect about 6 or 7 joints. For each six joints, there is one joint reference frame. This joint reference frame has its own orientation, it has its own configuration, right, when you do it. But now the question is, how do we model it? How do we represent it? So actually, just the classical way is to use a Euler angles approach. Theta, rotate theta 90 degrees, rotate theta about 45 degrees something. Rotate X first, rotate Y first, second, then rotate Z third or something. You know, the question is, you have a possibility to rotate all axes, okay? Which axis should you rotate first? Is it X? Is it Y? Or is it Z? So just this sequence could be controlled by using the robot angular representations, Euler or Quaternion. Actually, that's just who, it's you who has to decide. Actually, just if you are a programmer, just depending on the benefits and disadvantages, you have to decide actually which one is better. For example, I could imagine if you have Euler angle, I could imagine there could be a possibility to get into either multiple solutions because of trigonometric functions. You know, this, for example, sine 30 and the cos 60 have the same value, right? The same thing, cos 60 and the sine 30 will have the same value, something like that. So, so the joint which is rotating at 30 degree and at 60 degree could have some, yeah, same solutions maybe. The other is you could also run into singularity problems. Singularity is undefined points, which makes a robot to be confused or computationally incapable to perform the operation. Okay, this is the specific operation. So in singularity, just you expect either there is undefined solution. Yeah, just there could be some undefined solution, or there could be so many solutions which confuses the robot at that point. Okay, then the robot will be confused just to take what, or there is no solution, or there is infinite solution. You know, there's a possibility because 30 degree, 30, 60, 70, something, you know, there are some. But if you have also some wrist configuration, you know, where you have rotation about X, Y, and Z, like these robots, for example, here it has wrist configuration. Here there is a wrist. Okay, there is a wrist. This wrist means there is a rotation about X, Y, and Z. This is here. Okay, so this means unless you have a rotation, okay, about fifth joint. Now, as it is now, you could have a rotation about, you know, you could have a rotation about joint 4, about joint 5, and about joint 6. Now, okay, without noting on the without this note, if you consider with the global reference frame, there is rotation about this axis, then is a rotation about this axis, and then there is also rotation about this axis. So I will assume this is, if I assume Z as a reference frame at joint 4, then rotate Z, rotate X, and rotate Z only, you know, compare with 4. This is rotate about Z. 5 is rotate about Z5, and this is rotate about Z6. Z4, Z5, Z6 are axis of rotation, right? But only if you compare with respect to 4, rotate Z4. For the 5, the rotation will become rotate about X4. For joint 6, it becomes rotate about Z4. So it is Z, it is Z X and again Z, ZXZ. Okay. Yeah. So just you could think like that. Okay. Is it clear this one pointers? Is it clear for all of you, or is it confusing?
Sorry, can you explain more? Thank you.
Which point specifically about this configuration?
Yeah.
Sorry, Mr. Sule. You are talking about the axes, and I understood that the robot, which axis is better for the robot to go first, but I couldn't get it, what you said about the priorities of which one goes first. Could you please repeat or to say something in more detail? Thank you.
Yeah, okay, so I will repeat, okay. Yeah, now just the point is actually when you have angular configurations, you know, for example, for robot wrists, maybe I have to go to the simulation. Now, the wrist configuration means this guy actually is a wrist. Now, this is wrist is, for example, joint, maybe joint 3. No, not joint 3. Joint 4. Yeah, this is this and this is doing the same operation, isn't it? Just both are doing the same operation. Look.
Yes.
Both are doing the same operation. So this is what? Because of joint 4 and the joint 6, you will have infinitive solution. Okay?
And why do we have infinitive solution?
Because now you have a kinematic model, okay? Assume you have a kinematic model, then the robot will be confused whether to rotate this one or to rotate this one.
Yes.
Just to do the operation.
Mm-hmm.
So just it is leading to a singularity, okay? Now,
so which one does the robot use first? The first reason?
Yeah, actually, that's what you have to. That's what you have to decide, of course. Actually, the robot's free to choose whatever, you know.
Yeah. So
but
based on so because it is tourists, the robot is free to choose which one comes first, right?
Which comes first is joint 4, of course.
Joint 4 because it is thicker, or why it is joint 4?
Yeah, actually, just here to choose between the joint 4 and joint 4 is here. Actually, joint 4 is here. Yes. At this point, joint 5 is here. Joint 6 is here. The motor is. Yeah. So now, actually, just the selection procedure may matter.
The what? Could you please pardon?
So just how does it matter is actually it depends how. Actually, first it depends on the amount of load. For example, if you have to manipulate a large object, 6 couldn't make the operation because it has maybe
low power, maybe.
Yeah, less power as well as less rigidity, right? So this time this will make sense because it is more rigid, okay? Yeah, more rigid, and it could because yeah. Then the other time is actually if it is a small object, then yeah, this could make sense. But also you have to think about energy. if you have to manipulate this robot joint 4, then also it's indirectly means that you are using more power because of more inertia, right?
Yes.
So also just you have to think actually just which one you should have to rotate. When it performs the same operation, you know, provided there's a similar operation, then just you have a chance to choose from these two things.
Okay.
Mm-hmm.
Yes.
Good. Yeah. So actually, just robots could have singularity. Of course, it is because of so many reasons. Maybe, for example, one way is this is singularity. For example, you know, here it is undefined solution. I cannot move more than this. You know, this is singularity because
Excuse me,
undefined.
what do you mean by singularity?
Yeah, so just what I said in singularity is a state where the robot has undefined solution or infinitive solutions, or or it is a place where the robot gets confused. Okay, it will get into confusion because of one, undefined solution, second, because of multiple solutions, or because of no solutions. Okay, for example, now there is no solution for this robot just to move beyond this. So this time just it could be.
And how we know that there is no solution here? Because I see that you are moving the robot. So
Yeah, just is simple, right? Just you want to reach this object.
okay.
Simple, right?
So it's far away. So
Yeah, so it is
the robot
undefined,
cannot.
you know.
Okay.
Now, if you give this point as an input to the robot, then the robot doesn't solve it. So it is undefined position. Then the robot says it is a singularity configuration.
Okay.
Not only that, if I put here, it is also undefined.
Yeah, because it's underneath the robot and cannot touch it there. Okay.
Yeah. And also, if I put it here, also it is undefined because the robot cannot make this motion.
Yeah.
Because of self-collision. Okay.
Okay.
Because it will collide with itself and then it cannot reach there.
Yeah.
But also not only this, maybe I will have some video which shows this. If you give me some time.
Excuse me, could you please show the multiple solutions as well?
Yeah, but let's just wait. You see now? The video at some places where the robot wrist is making a rotation while it is. This is singularity now. This is singularity. This is singularity. Multiple solutions.
Can is the robot trying to pick kind of object or something?
Just
or
the
because,
robot. Yeah, because the robot is confused which axis to select, you know?
Yeah.
Look, now it is being confused. It's confusing the robot. Look, it is making undesired. Yeah, this is also singularity. Yeah, you see what happens to the robot? It is shaking.
Like the robot doesn't know what he is doing, or
So now this is,
because usually the robot should pick something or pick an object, as you said, and the robot doesn't know how to reach the object if a singularity happens.
yeah.
Like there is a undefined solution, maybe the programmer hasn't defined how to reach the object, or it is in a lot of solutions. Yeah, I think it all depends on the programmer, but how he or she programmed the robots or have mistakes on that, right?
Yeah, actually, of course, it depends how the programmer programs, but when you program also, you have to think about it, because there are solutions actually just to avoid this singularity. The one solution is to avoid these angles where it happens, where singularity happens, because it is known, the
So you're talking
manufacturer will tell you this is a singularity configuration, so avoid this.
okay, so we have to choose like in a way that the angles that the robot's angles doesn't reach their maximum angle, right? Like their limitations, right?
Actually, just this happens when you have inverse kinematics. Indeed, if you have a forward kinematics, you already have a pre-calculated joint angles. Okay, so you say theta 1 is 90 degree, theta 2 is 50 degree, something. Okay, so you define pointers. But when you have inverse kinematics, you know only the position of the gripper. You don't know the position of the joint parameters, okay, or joint variables. So when you define these joint variables, you have to make some decisions. No, the robot should have to make the decision by itself based on the inverse kinematics model, okay? So when you model your inverse kinematics, actually, for the robot controller, you should have to take into account there are possibilities for singularity configuration, and this singularity configuration could be mathematically calculated. By the way, it is not it's not random. You know it mathematically. So just you have to mathematically derive and say if this is happening, then close or lock the robot system.
Okay.
Then it will lock the joints.
When we do inverse kinematics, there will be always in the many solutions in such a robot, because it have 9 or 8 joints. So when we do inverse kinematics, there will be lots of solutions every time.
Yeah, not every time actually. Just there is another modeling method which is called Quaternion, and in Quaternion space it will not happen.
Yeah, sorry, it's true, but I think the speech of Alireza is not complete. The solution for moving the arm of the robots is true that it depends on the programmer decisions, but programmer decisions inspired from our space, from our place that our robot placed. For example, imagine a robot will pick a dashboard of the car and put it in the car. When the robot pick the dashboard is so big, it doesn't, and we don't have any place to moving the arm of the robots, because maybe make accidents and make it damage for products that the robot pick it. So before picking and after picking, we have two decisions. We have to make two decisions that how our arm of our robot moves. and after pickings, our decision is more important than before pickings, because we are in dangerous to our product will damage or destroyed or broken.
I totally share your notion, and that is also right. Actually, yeah, the programmer has full responsibility actually just to decide about the behavior of the robot, you know. Otherwise, it may cause some problems. So it's not only a singularity, but also you have to take into account the reachability, working space condition, obstacles, then also speed, also safety factors. Yeah, just actually just how do you monitor the robot, just how do you control the robot in case there is emergency, or if there is unwanted entry into the robot system, and so many things. Okay, just we have to think about it. And also, what if there is a disruption in your operation? What if the conveyor, for example, fails to deliver the parts? Then how do you control the robot? Then how does the robot adjust its cycle speed, cycles time, you know, and so on. So these things should have to be yeah, considered, and it's true. Sometimes we have a very limited working space, very compact. So the robot should make only a limited joint movements, you know, while it is moving the gripper, there is a possibility that the arms are going to make collision with the workspace elements. So this time just you have to be sure that that's the robot, you have to be sure that just the motion of not only the gripper, also the motion of the other body parts, okay, other links, so they will not make any collision with the system at all. So that's also a very important point. Yeah, okay. So now saying this, there is this is actually just a simple multiplication of z, y, z, z, x, z, something. It is a Euler representation. Just only if you are interested, just you can look at the mathematics, but it is nothing. It is only mathematics. Then, as I said, there is the second option where you don't have this singularity problem. It is called Quaternion. Quaternion is an imaginary space which you cannot see and just decide. Okay, it is an imaginary. It is hyperplane in the space. It has 4 components: rotational vectors plus a scalar. Okay, it's as a scalar plus a scalar which is called magnitude, and then a vector. So this they are represented with this kind of equation: the magnitude plus the vector of rotation along x plus vector of rotation along y plus vector of rotation along z, or something like this. Or yeah, this is jk here is imaginary. Actually, it is imaginary plane, so it will fulfill the complex numbers. I mean, it is a complex number, so you have to think about a complex. For example, I equals to square root of -1, and the square will becomes -1, something like this. I think that is from algebra. So this Quaternion was represented after the work of Hamilton. Yeah, actually, it is old enough, but still it is very strong. Yeah, actually, if you are interested, you can look it, but I would like to focus on homogeneous transformation matrix and so on. So as we said, homogeneous transformation matrix You know, as I said earlier, there is a position vector and there is a orientation matrix. 3 by 3 matrix plus rotation matrix is 3 by 3. There is a position vector, which is 3 by 1. Now, it's not really possible to combine 3 by 3 with 3 by 1 in one matrix, because it will become 3 by 4. And the 3 by 4 matrix has really a lot of problems. One is it's not invertible. It's not invertible. So in order to make it invertible, just because now if you combine 3 by 3 rotation with 3 by 1 position, it becomes 4 by 1. No, 4 by 3 matrix. Okay, this line becomes 4 by 3 matrix. 4 by 3 matrix, it's not invertible, okay, because it is not full rank. Okay, the matrix has no full rank. So in order to make it invertible, we have to make it full rank, and then we add simple zeros below and 1 here, which is scalar, which is called scale actually in computer vision. This is normal. It's perspective matrices. This perspective matrices, S is scale of transformation matrix, and P is translation matrix, and R is rotation matrix. So from this, actually, we get a homogeneous transformation matrix, which is 4 by 4. Okay, if you get 4 by 4, then the life is easier than after, because you can manipulate your transformation matrix from one to the other. So accordingly, from the simulation environment, then we have positions X, Y, Z, and we have rotation about X, Y, Z, and these all are represented in a working frame here. And this working frame is a 4 by 4 matrix. It is a 4 by 4 matrix, and this 4 by 4 matrix will let you to calculate the points from via1 to via2. You know, so you could transform. So you could easily transform from this point to this point. So the transformation matrix. Just you could move from this to this point because of the homogeneous transformation matrix. And this homogeneous transformation matrix is represented by a Denavit-Hartenberg convention. Just that is the most frequently used modeling approach. And this Denavit-Hartenberg tells you the following 4 parameters. The first is AI. The second is alpha I. Third is DI, and the fourth is theta I. Okay, AI, alpha I, DI, and theta I. They are used to represent link lengths. Okay, Denavit-Hartenberg. Link lengths. Okay, link twist. Okay, link offsets. Okay, then joint angle. Okay, AI, link lengths. Alpha I, link twist. DI, link offset. Theta I, joint angle. Now, when we come to our model, this robot has, it has for each joint. Okay, now if we focus, I don't know if we could make, if we could access to the models. I don't know. Yeah, yeah. Okay, for example, here. Okay, so maybe I could make. Okay, so here. Now, just for this component, okay, for this component, we have, for this component only, okay, we have we have this component, right? This component is this component. For this component, what do you have? For this component, what do you have? You have link lengths from this to this point, from this center to this center, you have link lengths from this center to this center. Then you have link offsets. Maybe which we call it link offset is, assume the rotation about this is here, and here it is a rotation about this, assume it is here. So the rotation from this, the distance between this and this could be offset distance. Okay, maybe let's say this one. No, maybe not cylinder, maybe I need to this guy. Okay, so it is in the other way. So, you know, from this point, okay, where I have the cursor here, to the center of this guy here, there is offset. Maybe I could have a chance to measure it like this. Maybe here, maybe. Yeah, okay, I don't know if it's okay. So anyhow, just there is offset between this and this, which is offset. Then we have theta, which is joint angle, of the rotation, which is theta is just nothing. It is only these guys. These are thetas. These are thetas. These are thetas. And we have joint offset. Yes, we have joint offset. Twist angle is actually now from this, okay, from this to this, there is a twist angle of 90 degrees. There is twist angle. It is twist angle is offset angle. There is an offset angle. Okay, this one is rotating this way, but this is rotating this way, which is opposite, which is 90 to each other. Okay, which is 90 to each other. So this is offset angle, which we call it twist angle. And yeah, now just we have the offset distance, offset angle or twist angle, then joint angle, which is this is joint angle. The difference between this and this is offset angle. The difference between this, yeah, now just we make everything all. Look now, this between this and this 90 degree offset. Between this and this 0 offset. Between this and between this 90 degree offset. Between this and between this 90 degree offset. Between this and between this 90 degree offset.
Sorry, Mr. Tuli,
Yeah.
how we deal with this information in our exam, you know, is a little confused us about exam, how we face with these lessons in our exam.
Yeah, just this is this will not on every exam this question was there. So these are parameters. Actually, just it is not about the lettering, it is about the concept. Okay, so you have to understand the concept. What is really link length? Link length is the length of the link. Okay, nothing. What is link twist? Link twist is the offset angle between previous frame and the current frame. Third, What is link offset? Link offset is the offset between the first link and the previous link and the current link in from the rotational axis, you know. So it's just how the links are offsetted from the axis of the previous rotation. The joint angle is a rotation of the joint variable, or it is a joint variable. Joint angle is a joint variable. Okay, it is theta. Now, actually, Kinematics has two conventions. Actually, one is classical convention, and the second is modern DH convention, or which they call also modified convention. Yeah, just they have different matrix formulation, but the message, or just the core message is the same. Finally, you will have the same result. Actually, just whether you do it in classical approach or modified approach, finally, the robot will perform the same operation, okay? But it is a matter of the order of multiplication, because it is a matrix. You know, in matrix, what you do really matters, right? So which one do you multiply first? Which one do you multiply second? If you multiply first this and this, then in the next step, you have to do this and this. This is a procedural difference, okay, between the Denavit-Artenberg classical and the previous approach. So just for example, just to mention it, there are a definition of this for variables. Again, let me repeat. AI is the length of the link I, which is measured along xi. Because we have so many joint variables, right, for the robot here, for example. So we have to explicitly say that this is length. Because we have so many joints here, we have this, 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 we have this. Now assume KRK4. Okay, for KRK4, according to KRK4, then now you could see this. Now AI is according to KRK4. Yeah, so now according to KRK4, AI is the length of link I. So A4 is the length of link 4, which is measured along X4 axis from the point where X4 and Z3 intersects to the origin of frame 4. Alpha 4 is the link twist, which is measured between Z3 and Z4 along X4 axis in counterclockwise direction. Counterclockwise is always, we use counterclockwise to measure the positive rotations. D4 is the link offset measured about Z3 axis starting from the origin of 3 to the point where X4 intersects with Z3 axis. Theta 4 is the joint angle which measures between X3 and X4 along the Z3 axis in the counterclockwise direction. So this is how you define it actually. Yeah, just you have to understand this. Just you have to understand, and then also just look with the example. Just it's not only reading the theory, but it is just you have to be able to interpret it, okay, in your own language. Just it's not only, of course, how you define it matters, but how you understand also matters a lot, because when I look at this robot, just I should be able to define it, okay, what is offset angle? For me, just looking at the robot, if the you know, if I will measure this one and then just check this one. So I have a twist angle for joint 2, which is alpha 2 is the link twist, which is measured between Z3, no, between Z1 and Z2. Yeah, because that's why I have this offset. It is, I'm now moving on the Z axis, right? So it is only rotating Z axis. So Z alpha 2 is the link twist, which is measured between Z1 and Z2 along x-axis. So I have now twist angle here. That's why I say I have twist angle of 90 degrees. Then how much is the value? So between this and this, I have 90 degrees. So you have to understand it, just you have to internalize it, okay? Just it should be inside your understanding, you know, just you have to understand it. Okay, so the other point is actually it is about the order and how it matters actually. Yeah, so in the classical approach, you have rotation Z, then translation Z, translate X, and rotate X. Do rotate first multiply Z, then first multiply rotation about Z, then multiply with the translation about Z, then multiply translation about X, then multiply rotation about X. This is order of representation, and then you get the matrix which looks like this. If you do the mathematics of the previous equation, you will get something like this. Then the other says first rotate X, then multiply with X, then rotate Z, and then multiply with Z. This is also a convention. When you do this, then you will get something like this. But finally, the total output will become the same. Okay, finally. So yeah, so it looks like this. Yeah, the forward kinematics then is a multiplication of the first joint, the second joint, the third joint, and then finally goes to the nth joint. That's actually how it works. The details just we look at next time. If you have any questions or something, just now you are welcome